So now that we have an idea of how this integrating factor method works, we're going to take it out for a spin and try to solve a differential equation. Specifically in this case, we've got a differential equation in terms of y and x, and we have an initial condition. So really we're going to do two things. We're going to use the integrating factor method to find the general solution. And the general solution for this is going to be y of x. And then number two, we're going to use our initial condition to get the particular solution. So just a reminder, this is a problem that we can solve in other ways, right? We have the lucky guess method, right? The method of the undetermined coefficients, and that would work to solve this. But the integrating factor method, a lot of people find it to be more satisfying. So we're just going to kind of follow the steps from before. The first step, if you remember, was we're going to rewrite our differential equation and get all of our dependent variable terms on the left. So dy dx, add the 2 over x times y. Now again, I'm leaving it as 2 over x times y because it's going to be easier for me to see what my g function is. What's left on the right is just 3. So that was step one, and now I can kind of off to the side say, ooh, this is going to give me my g function, and this time it'll be g of x. And that's going to allow me to find my mu, my integrating factor, mu of x in this case. And I can figure out what that is by taking e to the power, the integral of the g function, 2 over x dx. Now that is the same thing as e to the 2 natural log x. Now I'd love to say that this is the same thing as 2x, but that's not the way e and natural log work like that. So I have to pull that 2 inside and make it e to the natural log of x squared before I can use my exponent and logarithm trick. That's the same thing as x squared. So it turns out my integrating factor is x squared. So for step 2, now that I've got my integrating factor, I'm going to take x squared and I'm going to multiply it by the whole equation. And we can kind of simplify as we go. We wind up with x squared times dy dx. Plus, this becomes 2x times y. And then 3x squared. Probably the number one place where people screw up the integrating factor method is they forget to multiply both sides of the equation. Instead, they'll just multiply this side and just leave the other side alone. I see that a lot. So now what we have to do is rewrite this in terms of the product rule. And if we did it right, this should be the equivalent of, in step 3, the derivative with respect to x, in this case, of my integrating factor, x squared, times y. Now just verify that that's indeed what we have. When I take the derivative of this, it would be derivative of y times x squared, there it is, plus the derivative of x squared times y, which is right there. So it worked. The other side, still 3x squared. And now that I've got that sorted out, I can use my integration powers. And when I integrate this side, it's just x squared times y. And the other side is now going to be the integral of 3x squared dx. Not a terribly tricky integral. This is the same thing as x cubed. And I'm going to put all my constants in one basket here. And now I've got x squared times y equals x cubed plus a constant. And so I'm going to divide both sides, not subtract, but divide both sides by x squared, and I'll get my general solution. And I guess this is step 5 where I'm solving for it. But I'm going to get my general solution, which is just going to be x plus a constant times x to the minus 2 power, right? Divided by x squared, the same thing as the minus 2 power. Now I'm not done because I can find my particular solution. So I'm going to use my initial condition, which, if you remember, the initial condition from up above was y of 1 equals 5. And so I should be able to say 5 is what I get when I plug in 1 for x. That's 1 plus c times 1 to the minus 2 power. Well, 1 to the minus 2 power is just 1. So that means the value of c must be equal to 4. So, after all that work, we have our particular solution, which is y of x equals x plus 4 over x squared. Or you can say 4 times x to the minus 2. Now, at this point, we can verify it, right? And we could verify this either by subbing it back in or by trying it out on Maple. And I've already got it queued up in Maple, so that's what we're going to do. But just a reminder, you can verify this by taking your y of x right here, the x plus 4 over x squared, and then going back to your differential equation and subbing that in for y here and here, and proving that it does, in fact, produce a true statement. As long as it does, that means it's a solution. So let's take a look on Maple as to what's going on. Here's the equation typed in. You'll notice I put it in squiggly brackets there, meaning that we've got an initial condition, so it's an IVP. I hit enter. It thinks about it for a second, and then it tells me I got the right answer. So I'm happy. Yay! So let's take a look at one more example. Switch back over to the dot camera here. Let's take a look at one more example. And this one is not an initial value problem. This is just a plain old differential equation. And it says, please solve. Well, it doesn't say that, but I'm saying that. So what are we going to do? Well, just like we did before, we're going to follow the rules. We're going to use our integrating factor method. And so I'm going to start off by rewriting this. Now you'll notice this time I'm not going to write down each one of the steps, but I am going to identify the steps as we go. So my first step is I'm going to rewrite this thing. So we have dy dt plus 1 over 1 plus t times y, and again I kind of separated it out there, equals what's left on the other side is just t squared. So without much trouble, because I separated it, I've got exactly what my g of t is equal to. That is 1 over 1 plus t, or I'll call it t plus 1. It doesn't really matter. Right? If that's g of t, then that means I can find my mu of t by taking e to the power, integrating that, the antiderivative of 1 over 1 plus t dt. And that's not such a hard integral for us to do. That's the same thing as just e to the natural log of t plus 1, or just t plus 1. Right? After you cancel the e and the natural log off. So that means our integrating factor is t plus 1. So in my step 2, I'm going to multiply the whole darn shooting match by t plus 1, or 1 plus t if you want to list it that way. So let me switch back over to my blue, and I'm going to multiply the entire equation by that. I switched it to t plus 1. It doesn't matter. Now when I multiply it through, notice what happens in the second term. The t plus 1 on the top and the t plus 1 on the bottom kind of cancel. So I have t plus 1 quantity times dy dt plus just plain old y equals t squared. Now if I did it right, this left side should be entirely, should kind of boil down to the product rule derivative of my integrating factor times So t plus 1 times y. If I did it right, that's what it should be. Right there should be the derivative of this. So that was my step 3. And you can double check it at this point and say, well, if I took the derivative of this product, it would be this thing times the derivative of y plus the derivative of this thing times y. And sure enough, that's what we see in the previous step. So next step, I get to do the integration. And integrating the left side kind of integral and the antiderivative and the derivative sort of undo each other. And we're just left with t plus 1 times y. And I'm not multiplying it through because I know I'm just going to divide by it anyways. The other side, I've got an integral now of t squared dt. And at this point, I really hope some of you are like, wait, stop. What have you done? You forgot something. What did we forget? Hit pause. Look at it. Do you see it? Remember in the last video, I said the place where people, or the last problem, I said the place where people mess up is they don't multiply this through to the other side. And sure enough, I didn't multiply it through to the other side. Right here, it's t squared times t plus 1. This is times t plus 1. And inside that integral, it's times t plus 1. At least we caught it. But it happens, right? And if you did, you get to the end and you'd check your answer and you'd find out, oh, that doesn't work. I must have screwed up somewhere. So now I get to integrate. This side is just kind of hanging out for right now. I get to integrate this. And that's not terribly difficult. This is just t cubed plus t squared. And so that's really kind of two separate integrals. And so that's just going to be 1/4 of t to the 4th for the first term, plus 1/3 t cubed for the second term, plus a constant. And that constant comes from both of those integrals kind of together. So this side is still t plus 1 times y. And the last thing I have to do is just divide by this factor in front of it. So 5, I'm just going to write my solution, y of t equals the right-hand side all divided by t plus 1. Now, you can get fancy and try to factor this thing and do that, but in the end, it's just 1/4 t to the 4th plus 1/3 t cubed plus constant c all divided by t plus 1. Now, at this point, you might look at it and go, ugh, I don't think I want to take its derivative to be able to plug it back in to check the answer. But you can verify it. And I write down at the bottom, always make sure you verify. So let's hop on Maple and see if Maple says we got the right answer. So here's the solution, or here's the problem that I typed into Maple. Make sure I did it right here. Looks good. So now I'm going to hit enter. And Maple says, hey, what do you know? Maple came up with the exact same answer as we did. It turns out Maple recognizes that this is a linear differential equation, and it uses the integrating factor method as well. Turns out the integrating factor method is a pretty convenient way of solving linear non-homogeneous differential equations. So back to the notes page. Since we know we got it right, we verified it. We could, if we wanted to, use an initial condition to come up with a particular solution, but that's all we had to do for this particular problem. So I'm going to stop the video here. We've got one more problem left in this section, and it's an application problem. We're going to be going back to the mixing tank for this one. So see you for the last video in this section.